let's regroup. We'll talk like John Doyle and the acne and other molecular trap.
Yes, okay. Well, thank you very much for the invitation. I have to say, I will apologize here that I will not be here this afternoon. Being a local, I have local things to do like teaching and postdoc lunches that were scheduled a long time ago and such of that. So I do apologize, but it's been very, very interesting so far, and I'm sure that this afternoon will be fantastic. So I'm going to talk about cold and ultra-cold molecules for, I just made this up, it used to say particle physics until 10 minutes ago, then it said cosmological particle physics. But you'll see it does have a connection with cosmology. So take a step back. What we do in AMO is we couple the quantum systems, things like atoms or spins. And the first thing that you notice when you do this in the laboratory is that these resonances can shift due to external perturbations. That can be turned around and turned into sensing, as you've heard about. Here's a classic example of MRI, but also gravity gradients, etc. So really, the kind of spectroscopy of doing spectroscopy on objects like this immediately leads to sensing. And the title of my talk is Cold and Ultra-Cold Molecules, and I'll just give you a brief overview about what's been going on. Research with cold molecules is growing. There's no question of that. Why? Why do research with cold and ultra-cold molecules? Well, one very simple answer, I'm going to give you two general answers. One is the universe is made of molecules. So if you're doing fundamental research on molecules, it connects that.
5%. Only 5%.
Yeah. It's even worse than that, right? Most of it's just atom. Yeah. All the good stuff is made of molecules. So it connects with atmospheric physics, space physics, of course, and biology. Now, why cold then? Right? Well, here's a very simple answer. When you cool molecules, you get phase-space compression. And this is not really a big deal for atoms at all. Atoms that come out of an oven, they're pretty much in the ground state, more or less. There's some hyperfine states, what have you. But molecules have all these other modes. They have vibrational modes and rotational modes. And so that, say if you have a molecule like this is anthracene that comes out of an oven at, say, around 1,000 Kelvin, it's got about 10 to the 15 different occupied states. What I mean by that is if I have 10 to the 15 anthracene molecules at that temperature, each one, on average, is in a different quantum state. And if you think about doing spectroscopy on such an ensemble, it's really bad. It's bad because the signal is incredibly low for a given transition. And also, you've got Doppler broadening, all sorts of problems. However, just by cooling the molecules down to around 1 Kelvin, you can get about 10 to the 10 orders of magnitude. 10 orders of magnitude. 10 to the 10 orders of magnitude would be great. 10 orders of magnitude phase-space compression, and your lines narrow up, and really you start looking at this kind of thing more like an atom, and I'll show you what I mean in a second. So there's a method to do this, to cool any molecule at least up to about human hormone size to around 1 Kelvin. It's buffer gas cooling. You have to tune the system right, but more or less you just inject a hot molecule into a buffer gas of, say, helium. Excuse me, for going to 1 Kelvin, it is a buffer gas of helium, and that helium is cooled by a wall, which in turn is cooled by a refrigerator. So that's really great. I also will mention that you can do spectroscopy on these molecules in this cell. Typically, these buffer gas cells are about that big. Or you can pop a hole in the cell and extract these molecules in a beam. This is called a CBGB, cryogenic buffer gas beam. And anything that you can cool, you can extract in such a beam. So this works really well. I will say, I left the slide out, so I'm going to go back. This kind of beam for radicals is about 1,000 to 10,000 times brighter than previous molecular beams for radical species. And the reason is because the cooling is not coming from some supersonic expansion. It's really coming just from collisions inside the cell. So it turns out this whole technology is incredibly efficient. So you squirt in molecules into the cell, no matter how you do it, through ablation or injection, at least 10% of them basically make it out the hole. And the radicals are bouncing off of helium. They don't care. The helium doesn't affect it. Just cools it both rotationally, vibrationally almost all the time, and translationally. So if you just do spectroscopy, here's his rotational microwave spectroscopy. There's also work that was done at Gilla with infrared cavity spectroscopy, which we collaborated on a bit. But the basic idea is, here's microwave rotational spectroscopy on molecules like this. You get these very, very narrow lines. What it is, on one hand, it's a fingerprint of the molecule. Any molecule will have a very specific set of lines, just like an atom. And therefore, if you have a mixture, say a mixture of all this stuff, and you put it through a microwave spectrometer, you'll see these lines, but you can easily tell what's there. And these lines don't overlap, right, except in the case where you have a very, very large number of molecules in the mixture. And so this kind of approach generally has about 10 to 100 times higher signal than previous methods. And we've been used it to study conformational relaxation, doing chiral spectroscopy. You can use microwaves to do chiral spectroscopy, etc. But also what I want to point out is that if you're making a spectra like that, that means that you're going to be able to control these molecules. If you have spectra lines, you're doing spectra, the next step is control. And so you wonder, looking at spectra like this, can someday we have complete quantum control over that? Complete quantum control means ground state, everything, and then you can put it in whatever quantum state you want. So we can imagine it, what it's good for. It's so far out there, it's not exactly clear what it's good for. But you can imagine that this is the future that's coming. So that's one reason for cold molecules. Another is that although cold atoms are proven systems, molecules are actually qualitatively different and more complex than atoms. For example, you have this electric dipole, but that's not the only thing that you have. You also have vibrational states and some other things that I'll mention in this talk. For example, this. With molecules, one has this orbital angular momentum possible. With molecules, it's possible to have orbital angular momentum along the internuclear axis. Now, for diatomics, it's actually very rare. We use a molecule that has this in the Acne experiment, which I'll talk about. But for polyatomic molecules, this is completely generic. And I try to connect with people's pasts. You may have heard of the K quantum number, which is the quantum number for orbital angular momentum of a symmetric top. If you haven't, don't be embarrassed. It just means you're a real atom person. But chemists know this quantum number. And it really, what it means is that you have two opposite parity levels that are very closely spaced. So except for high order perturbations, these are degenerate opposite parity levels. And what that means, as you know, if you have a diatomic molecule, just a normal diatomic molecule, not with orbital angular momentum along the internuclear axis, you know that when you apply an electric field, you align the dipole in the lab frame, and this comes from the mixing of the opposite parity states, which are the rotational states, n equals 0 and n equal 1, for example. However, when you have these quantum numbers, you get, and so for the regular diatomic, you get this kind of alignment of the molecule as a function of applied field. Okay, and the reason is you start aligning it, and then you start mixing in other rotational states. But if you have this kind of structure, that's not what happens at all. What happens is you get this kind of 99 with 6-9 alignment with totally reasonable applied laboratory fields. And you have three states. You have a state now in the lab frame with the molecule pointed this way, and then a zero dipole moment state. This is qualitatively different than what you can achieve with atoms. And so this is very, very useful, and it's completely generic for polyatomic molecules. This feature is an important feature for ideas on how to use molecules for quantum computing, but also for doing precision measurement. Okay. So again, answer 2, I'll just expand on this. There's a lot of physics. Most of the work with cold molecules has so far been driven by this, quantum simulation and information. There's lots of theory about how molecules can be used to do, simulate spin lattice Hamiltonians, make quantum computers, etc. I've always been interested in collisions in chemistry. There's some fundamental questions about collisions that we just do not know the answer to. And I mean, they're really very fundamental about cold collisions. And then I'll be talking about precision measurements. One precision measurement, germane to this audience, is what is the dark matter? We know it exists. And there's been some proposals, and I'll tell you about our proposal in a second, for using molecules to look for ultralight dark matter. And thankfully, we have this wonderful introduction about this. But the basic idea is the ultralight dark matter can cause a time variation in fundamental constants. Those fundamental constants will change the behavior of these particular quantum states within the molecule. You measure those precisely, you measure them versus time, and then you can actually look for ultralight dark matter. There's a number of references here. But I'll just point out one particular example. This is a paper that we put on the archive, 2018. It's still under review at PRL, but it's all our fault because we got the reviews back and we just got busy. So, isn't that, yeah, it's the first time. And so it's all our fault. I'm not complaining about PRL whatsoever. It's actually nice that they're being so patient with us. But we will resubmit it soon. There were some comments that we needed to address. So the basic idea here is that you're using this more complexity in this even triatomic molecule. There's kind of an accidental degeneracy between these two vibrational ladder states. Wondering how to read these numbers. There's this stretch mode. That's the first number. There's this stretch mode. That's the last number, and this middle number is a bending mode. And so you have this near degeneracy, which means to go between here and here. It's a microwave transition. It's not an optical transition. And if you have a change in fundamental constants, this mode will behave differently than that mode. It's as simple as that. And you can come up with other examples, and it has. There are other examples that have been talked about. We're not the first people to think of this by any means. But this particular approach that we were talking about that can use laser-cooled molecules, which I'll talk about later in this talk, has a very high sensitivity, and that's the idea. Oh, by the way, that was SROH, strontium monohydroxide, that has this. But you can really, I'm sure there's other molecules out there. This particular molecule we're interested in using for this purpose for a technical reason, which I'll get to later in the talk. So that's one of the mysteries, two big mysteries. There's maybe 10 big mysteries, but anyways, here are two of them. One is dark matter. Another is the matter-antimatter asymmetry. Something happened around 10 to the minus 10 seconds. In the expansion of the universe that led matter to dominate by a very small amount over antimatter, about 1 part in a billion. So the question is, why did that occur? There's a generic theory by Sakharov, which has a few ingredients, like 3 ingredients, but one of those ingredients is CP violation. And the CP violation that we see in the standard model is not enough to explain the matter-antimatter asymmetry. So there should be some new physics out there to describe this. So we need, beyond the standard model particles, and associated CP violation, or something else really new, right? There could be something else that's going on that we haven't thought of. Same thing with these dark matter searches. It's like, yeah, okay, this is great. We're going to look for axions or heavy stuff. Doesn't matter. It could be wrong. Could be something else, right? We just have to recognize that, be open to new ideas. So here's the depiction of the standard model. There it is. There's a rule book, and there's these particles, and the standard model describes all lab-based particle experiments. That's great. And a possible solution to those problems, the dark matter problem and the matter-antimatter asymmetry, is that you add these other new exotic particles. They're exotic looking. Supersymmetry is one of the kind of the baseline theories. We'll call it a kind of generic theory, which we can interpret experimental results from. Supersymmetry, as you'll see, is not to be joking about it, but is not as natural as it used to be. So you can look for these particles, these new particles at a collider. That's done, and this big machine here, the LHC, tries to create these beyond the standard model particles, and it has kind of it creates particles up to around 1 TeV mass. Okay, and the next generation would go up to about 10 TeV. This is just a sketch. It's not clear who's going to build this, but if it gets built, it'll probably be built in China, and this is probably an underestimate of the cost, something more like 50 billion. So, well, if those particles exist, you can try to make them, but you can also just bask in the fact that they're inside your body, hovering around the electron. And these virtual particles that are there because of the high electric field around the electron changes the properties of the electron. In particular, these particles, which are generically expected to have CP violation associated with them, would give rise to the electric dipole moment of the electron. And so that's what we want to see. That's what we want to look for. And by looking for that electric dipole moment, we're actually looking for these CP violating particles with the CP violating phase phi here. That's the idea. One of the nice things about this approach is the standard model particles give an EDM about 10 to the 10 times lower than current experimental values. That means within the standard model, as far as we know, as long as the calculations are right about the standard model, it's 0 background. So if you see an EDM, it is beyond the standard model physics. One can estimate, using the kind of atomic physics kind of point of view, what the size of the electric dipole moment of the electron is based on the magnetic moment, and then there's a scaling between the mass of the electron and the mass of this new particle. There's a CP violating phase, and this is the loop term. The number of loops, if you're in a single loop, this is n is equal to 1. So there's a 1 loop diagram. You can go to 2 loops or 4 loops, whatever you want, and you'll have some particular sensitivity. Turns out, very interesting, as I'll point out later, the 2 loop diagrams are actually of very high interest to us. I'll show you why. So let me talk about the Acne experiment. Acne is looking for these particles, and here's our mascot, and here's our equipment. So the idea with Acme is that there's a molecule, thorium monoxide. It does have orbital angular momentum along the internuclear axis. Okay, we'll use that fact. The effective electric field inside this molecule is around 10 to the 10 volts per centimeter, which is great because the total energy shift of the electron will be the dipole moment times the applied external electric field. Times the field that the electron feels inside of this molecule. So we can take this molecule and we can put it into an external electric field, EZ. What will happen is that these states will split. They'll split by an energy which is 2 times the dipole moment of the molecule. This is capital D, the dipole moment of the molecule. And because of this orbital angular momentum, these things are completely aligned. I think it's like 5 nines alignment. And these states here are for the molecule pointed in the up direction, if you will. These states are molecules pointed in the down direction. Sorry for the computer error here. This is n tilde. This is not meant to be the n quantum number for rotation. It's our own personal n tilde is basically just the orientation of the molecule, whether it's pointed this way or this way. So that's what happens when you put it in an electric field. And here's the electron sitting inside the molecule. This state of the electron is down. This state of the electron is up. If we add a magnetic field, it interacts with the magnetic moment of the electron. You get this energy shift, which is the same as spin precession. And if there's an electric dipole moment of the electron, little d sub e, then you will also get a shift, but that shift will be in an opposite direction depending on whether you're looking at this manifold of states or that manifold of states. So that's the idea. And you do the experiment. You do the experiment by looking at the spin precession of the electron and doing what we call switches. So a switch here is very easy to describe. We can switch between using the molecules oriented this way, and then we leave everything else in the experiment exactly the same. We don't change the electric field, the magnetic field, nothing else. We don't change the web page that we're looking at. Everything just stays exactly the same. And then we do the experiment again, and then you can subtract out any effects due to like variations of magnetic or electric fields by doing this method of switching. You also do the traditional method for EDM experiments. You also switch the electric field back and forth, and you also switch the magnetic field back and forth. And so you have these 3 switches, and you do 8 combinations, and you can extract from that very accurately this electric dipole moment of the electron. Here's the experiment. Here's the CBGB of thorium oxide. This was Acme 1, so this was the one we started in 2000, right around 2000. This is Acme 1. It's an old school molecular beam experiment. You create the beam We use optical pumping to align the spin, and then we use optical readout to figure out how much the spin is precessed. How do you do this? These are transparent electric field plates, and lasers go through here. And I think I've got a picture. Yes, here's a picture now, not of Acme 1, but of Acme 2. So we got a result in 2014, which was an order of magnitude improvement over the previous limit on the electric dipole moment of the electron. Acme 2, we got a result in 2018. This is what it looks like. There's the CBGB. Here is magnetic shielding, and our molecules fly for a time which is about 1 millisecond. This guy's starting to... All right, so it's about 1 millisecond coherence time. And it works exactly as I described, the spin, molecular beam spin precession experiment. So this isn't everything in the experiment. We also have a lab which has got some more lasers in it. We also have a radioactive tent to make our targets. They're slightly radioactive. And we have, well, that's it. We have some offices somewhere. So in 2018, last year, we improved the limit on the electric dipole moment by a factor of 10, down to 1 times 10 to the minus 29. This was the team that did it. This is everybody. And Jing is here in the back of the room. I don't know if anybody else is here. I don't think anybody else is here. You may see Zach around today. And if I didn't mention before, this is a collaboration between 3 PIs, Dave DeMille at Yale, Jerry Gabrielis now at Northwestern, and myself here. Nick Hutzler wasn't involved in this experiment very strongly, but also continues to be involved. He's now a professor at Caltech. So what does it mean? So what do these limits mean? I will just want to emphasize first that I'm going to show you some interpretations within the SUSY framework of the EDM limit. These bars here that you're going to be looking at, these are specific calculations. So these are, real live theorists, high energy type theorists, particle theorists that calculate, well, what does it mean? What does that limit that we put on the electric dipole moment mean? And here it is. So here we're looking now for the impact that Acme 1 and Acme 2 had here. These are one loop calculations for leptons. These are supersymmetric partners of the electron, for example. Here's 2 loop calculations for the stop. Now, if you're familiar with the LHC and particle physics, that's kind of their key target is the stop, supersymmetric partner of the top. And but through these 2 loop, you don't couple directly, but through these 2 loop diagrams, the electron does couple to the top stop particle. And so those calculations show that with order of unity CP violation, there's no reason to think it's anything but order of unity, and there's good reasons to think that there's CP violation out there due to the matter-antimatter asymmetry. But nonetheless, there could be some conspiracy, and that phase could be very, very small. We assume it's order of unity, and that gives a limit around 5 TeV for the stop. That means if it exists with CP phase 1, it's going to have a mass greater than 5 TeV. For the leptons, the supersymmetric partner of the electron and associated particles, it's up around 30 TeV. I do want to point out that the nuclear work has more sensitivity to these particular supersymmetric partners, but also through the 2 loop diagrams also has sensitivity to the stop. And so the sensitivity of the nuclear EDM experiment, the Mercury experiment by Blaine Heckel in Seattle, it actually also has sensitivity to the stop around the same range. So that's the thing that's great about these 2 loops, is that you really have this very, very broad sensitivity to a whole wide range of new physics. It's not just some kind of narrow, okay, I'm testing this one particle or this one model. It's very broad. So here's now the EDM along this axis. Here's a number of theories that have been proposed. Of course, there's SUSY. Here's naive SUSY. And even before we got into the game, it was kind of under stress. And here's the 2014. I'll mention the Gilla experiment 2017 in a second. And here's Acme 2018. I'm going to do a direct comparison with accelerators, because under the CP you already use CP violating phase, we can do this. Here's the LHC ultimate direct stop mass reach right here. You can look up this reference. Here's time in this direction, and you can see how the accelerators were moving forward. The mass reach is less than the accelerator reach because you've got quarks in there, so they share the energy. That's why there's always a gap. So that's what accelerators look like. What did EDMs look like over the same period of time? Well, there was progress that was made. Now we have this excellent theory to interpret this fairly simply. Here's a two-loop limit. Sorry, this is the implications for two loops. Here's the implication for a single loop. Here's Acme 2 here. And this is what has happened over time. We lay those on top of each other, and now the EDMs have kind of crossed this line. And so you can kind of see that as time went on, the EDMs were kind of in the same ballpark, but really now for this order of unity CP phase, it's well above the LHC. So how do we improve acne? Right? We want to improve it. We want to improve it we'd love to improve it through squeezing. We don't know how to do that, but we do know how to increase the number of detected molecules, and we know how to actually increase the coherence time by making this longer, this interaction region longer. So the way we're going to increase the number, I'll get to the full table of improvements in a second, increase the number, is by using a electrostatic lens to focus the molecules out of the source and into the interaction region, just capturing more of the molecule solid angle than we did before. So here's the basic idea. Here's the molecular source. And here's some trajectories showing how this molecular lens will focus the molecules into our interaction region. So without the lens, fewer than 0.04% make it to our detection region, and we hope to improve this by about an order of magnitude. Theory said simulations say about a factor of 16 gain. However, I should say back here. However, for this to work, we need to put the molecule not in the ground state where it comes out. That electric dipole moment's not high enough. We need to put it into another state, which ideally has a very high electric dipole moment. This is now the electric dipole moment of the molecule. And there's this Q state, which has this very high electric dipole moment. And that's what we want to do, but we have to get it there. And what we've done recently is use STIRAP to drive the molecules into this state, which is called the Q state. It's just a molecular name. It's called the Q state. And what this data is showing is that we can get with about, I want to say, is it 90%? Yeah, 90% efficiency, get the molecules into the Q state. Then we haven't focused them yet, but we can get them into the Q state and back out with 90% efficiency. And so this is a really huge step in being able to try to improve our flux. The next thing to do is to build a molecular lens. So we have now advanced acne. That's what we're working on now. And there's a number of things that we're doing to improve our signal. One is our EDM sensitivity. One is we're lengthening the interaction region. We have this electrostatic lens. We're upgrading our detectors. And it turns out we already figured out a noise source that had an effect on our previous experiment. We figured out how to solve that too. So you put that all together, we should have a sensitivity gain for advanced acne of more than an order of magnitude. And that would put us up here, up around 10 TeV in two loop. How do we improve beyond acne? How do we get there? We're still stuck with this unless we do squeezing. And the question is, can we come up with a system where this is improved and we can do squeezing? That would be very nice. So we want longer coherence time. Acme is around 1 millisecond. Coherence times in the lab for ultra cold atoms is on the order of 10 seconds. So that would be very nice. There's already 2 EDM experiments that have much longer coherence times. There's the Gilly EDM experiment, where the molecules are held in an ion trap. Other than that, the basic structure of this molecule is like THO. Okay, it's got an omega doublet. You polarize it. It's not exactly the same, which is good because if you get it's got different systematic effects, it's good to have 2 different experiments with 2 different systematic effects. But one of the big advantages of this approach is that these molecules are sitting there. And so you can interact with them for 1 second, 10 seconds, get a very long coherence time. Here's another experiment, although it hasn't made an impact it's not near the same limit for the nuclear EDM or the electron EDM as other experiments, is really showing the way. Here the idea is you take radium atoms and then you put them you laser cool them and put them into an optical dipole trap. So again, you get this very long coherence time. And this is being done at Argonne. Matt Dietrich is currently leading that. So we want this kind of long coherence time. We want to have ultra-cold molecules in order to do that. As I mentioned before, the field is really driven by this, which is great, right? Because you've got a lot of people working towards making ultra-cold molecules. There's kind of two different ways of getting at it, and at least I'm breaking it down into these two different ways. If for using molecules for quantum simulation, one is kind of a top-down approach where you try to get a large phase-space density using say, evaporative cooling for atoms, and then you associate, or somehow creating the molecules and doing collisional cooling of some kind, and you get them to a very high phase-space density, then say fill an optical lattice. Another approach is by using optical tweezers, where you somehow or other create the molecules in the tweezers, and then you can then take out entropy, so to speak, by just throwing away the empty ones. You rearrange this, and this has been very, very successful for atoms, including creating quantum simulators for atoms. One way to make, I think I've got another slide here. Yeah, right, I'm going to skip. So one way to make these molecules in the tweezers, this being done by Conquan Nee's group here at Harvard, is you take two atoms and two separate tweezers and you bring the tweezers together, you bring the two atoms together, then you associate them into a molecule, and this has been quite successful. There's also many other groups that are doing, for alkalis and now expanding beyond alkalis, some kind of association. Here's a little grid here, lithium, sodium here, and then you can see what's been going on. This is actually now a year old, so it may not be completely up to date. But there's a lot of intense work, including at JILA, looking at dipole-dipole coupling between these bialkali molecules in an optical lattice. There's another method that we used. I won't say much about it, just mention it was used for a lot of collision work, including looking at spin-suppressed chemistry. There's also mechanical slowing, what we call a cryofuge. A lot of this work is done with all this work is done with supersonic beams and somehow mechanically slowing the molecules. Most recently, Edna Arvesius was able to do this with molecular oxygen and actually magnetically trap the oxygen and see collisions between molecular oxygen in this way. That's just the latest, but there's also work going on at MPQ using, again, things that you can get out of a bottle like formaldehyde. And then there's laser cooling. And the idea behind laser cooling, I'll take a little bit about the history, but this is the basic idea, is you have this CBGB, you want this nice slow, intense beam of these molecules, all of which are radicals. You do laser slowing into a MOT. The idea is to do suboptical cooling and then put it into an optical trap. Here, I'll just give you a few of the highlights of the history. 2004, DeRosa pointed out that a particular problem could be overcome by choosing the right molecule. What do I mean? Here is the molecule. If you're trying to laser cool, you're trying to cycle, say, 10,000 photons to get the energy out, slow them down, and then get them into a MOT. If you excite this molecule from this ground electronic state to this excited electronic state, most of the time, for the typical molecule, only some of the time does it go back into this ground state. Most of the time, after 2 or 3 photon cycles, it'll end up in these excited vibrational states. That has to do with the Frank-Condon factors. But for a certain class of these molecules, like calcium fluoride, then the Frank-Condon factors are highly diagonal, and it only goes into these other states just very rarely, and that means you can apply just a couple of laser frequencies to drive it back into this state and put it back into the cycling transition. So DeRosa pointed this out for a number of diatomic molecules, including calcium fluoride. You also have a rotational dark state problem. You can think of that as a vibrational dark state problem. These other vibrational excited states are dark to the main transition. But also you have rotational dark states. Basically, if you excite up, and after a few photons scatters, the molecule will go into some linear combination of these ground states, and it will again become dark. And what Ye pointed out is that you can use some kind of field to mix these states and therefore make it less dark. And Dave DeMille followed that up with saying that basically there's lots of different ways you can mix these states with microwaves or magnetic field, lots of different ways of doing it so that this dark state problem can be overcome. And then very quickly, DeMille showed in 1D laser cooling of strontium monofluoride. Then there was a number of other improvements, including, I just mentioned this, we did laser cooling of this molecule, molecule Z, right? So we keep you in suspense. What is molecule Z? You wonder.
Sounds like a new drug.
Yeah, there we go. And I'll tell you what that is later, and you'll see why I included it in this list. So this is up through around 2016. More results. So we embarked, and my group, on our first molecule we started to try to laser cool, which was not molecule Z, was calcium fluoride. And this is kind of the typical structure. Here's a ground state. Here's first excited electronic state, second excited electronic state. You can see the Frank-Condon factors are here, so very rarely goes into these other states, and we have like 3 or 4 laser frequencies to repump it. And we also use both this transition and this transition in our experiments. Oh, the Mott capture velocity is not, if you work with alkalis, it's not the same. It's very low. It's around 5 meters per second, and that's a huge issue. Nonetheless, we've created a magneto-optical trap of calcium fluoride. Here's our magneto-optical trap. These are RF Mott coils in order to get rid of this, this dark state, this rotational dark state problem. We flip the polarization of the Mott back and forth at a very high frequency, and we also flip the magnetic field back and forth at a very high frequency. So that's what's going on here. It's about 50 centimeters from here to here. Here's a CBGB. We slow down. We're using the green transition, and then we create a Mott using the red transition. You should also see this paper in the same year came out a bit early. The batteries are dying. That's why I'm having problems. The same year was from Imperial, and I'm hoping that if I replace one battery, it'll work. Oh, yeah. Oh, great. All right. I'm going to move through this very quickly because one of my points of showing this is to show you how far laser cooling of molecules has come, especially then leading into some of the experiments we're thinking about doing for particle physics and cosmology. So let me just say, these molecules are really, really hard to slow. They're kind of hard to Mott, but once you've got them ultra cold, in many ways you can think of them as an atom, but with these extra features. Okay, so with that background, you can say, well, okay, you've got them in a Mott. Next thing to do is to do gray molasses, right? Does gray molasses work for these molecules? Yes. It basically behaves like an atom. There are complications, but so the typical gray molasses, you turn off the Mott, then you put on light, which is subdoppler tuned, above resonance, blue detuning, and you can cool the molecules down now from around 1 millikelvin to around 50 microkelvin in a very short period of time. That's not a surprise. Of course, it's not a surprise. We don't know whether it would work, right? Because there are other complications, but it turns out that it's not that complicated. The other thing you can do is do velocity selective coherent population trapping, which is now called lambda enhanced gray molasses. But at least one person in the audience knows it's VSCPT, right? And so here the idea is that you can create this dark states by having 2 different polarizations. These dark states are velocity sensitive, so that if the molecule is moving at very low velocities, the 2 polarizations of light you'll create a dark state which will not interact with the light field. But then if the molecule starts to move, it'll go out of resonance with one of them, and then you'll start optically pumping again. And so you do this kind of random walk in momentum space. And when you find a low velocity, you stay there. That's the idea. This is now, as a function of this detuning, this is the differential detuning, this is the overall detuning, and what you're showing here is the different temperatures that we were able to achieve, and we were able to achieve temperatures around 5 microkelvin using this, this lambda-enhanced gray molasses, or VSCPT. The next thing to do, we're interested in collisions, but we're also interested in, this idea of precision measurement, getting things into optical traps so you can interact with them for a long time. And what we did was we put a optical dipole trap through the MOT, and what we were able to show is that this cooling, this VSCPT cooling, actually works inside the optical dipole trap so that we can load and enhance the density of the molecules in the trap. And so that worked extremely well. That was shown in this work. You can see here's the cloud, the MOT cloud, and then here's the optical dipole trap, that little dot, and we're loading the molecules into that. This lambda-enhanced cooling, you're scattering photons, which means that you can look at the scattered photons, you can image. And so we call this lambda imaging, and that's very important because we can scatter about 10,000 photons off of a given molecule before it kind of heats up and leaves the trap. So you have this very, very high fidelity way of determining whether the molecules are in the trap. That led to this, which is where we're doing single molecule, we're doing collisional blockade, we're loading single molecules into an array of optical tweezers. We're also now merging the tweezers and studying collisions between single molecules. So in 2019, there's 4 major groups here with a lot of progress. I'm going to go through this fairly quickly. Also mention that we're competitors, but we're also collaborators on this, as our group and Junye's group. And he's got the newest molecule, which is YO. And then this experiment here is a collaboration with 2 other people in the CUA, Wolfgang Ketterle and Kangquan Ni. This is our CAF experiment here at Harvard. So here is like a little plot of progress of laser cooling of molecules. Boy, am I way over time? Is that?
I want to know about the Z one.
Okay. Here's the density as a function of years ago, and it's been kind of steadily going up. This is the red is our calcium fluoride work. I can tell you what the other ones are if you'd like to know. Here's the phase space density, and so now if you extrapolate, here will be a phase space density of 1 in a couple of years. Who knows? But you can see that now we're fairly far along the development of laser cooling with molecules, I would say. So there's motivations for larger molecules. Of course, cold chemistry. There's a paper, including one from us, about using symmetric top molecules for quantum computation because of this orbital angular momentum along the internuclear axis, but also looking for beyond the standard model physics. So Team Molecule Z, we were working on CAF. It was like, well, let's try a polyatomic. Why not? So we started this in 2014. And we were able to do, this is now just regular Sisyphus cooling in 1 dimension for strontium monohydroxide, this dark matter candidate molecule. And we were able to show, here's the molecular beam profile with no cooling. We can tune our Sisyphus detuning so that we're red detuned and we get heating just like the textbook, and we got cooling. But the key point here, cooling down around a 1 millikelvin in 1 dimension. Key point here is that we can wrangle this molecule very similar to how we wrangle calcium fluoride. And as we were working from 2014 to 2016, we realized that the reason, there's a generalized reason, is that it's this bond that matters. So here's calcium and here's fluorine, and you have this ionic bond so that the electron cloud, both in the ground and the excited state, is away from this. So this electron is not participating in the bonding, it's just getting excited and down. And so the Frank-Condon, the bonding doesn't change, which means that the Frank-Condon factors are diagonal. So you can replace the fluorine with a pseudofluoride. And that means that you can put this on it, right? Or you can put something bigger on it. So you can think of this class of molecules we call MOR molecules, where we can just put whatever we want over here, and pretty much it doesn't change the laser cooling properties. And there's I would say there's 2 papers here. One from us, and also Isaev and Berger came out around the same time with the same idea. although for a different class of molecules. So what it means is that we think we can laser cool ytterbium monohydroxide. This is an MOR molecule. Ytterbium monohydroxide is an EDM-sensitive molecule. It has orbital angular momentum along the internuclear axis, which was absolutely crucial for both the Gilly experiment and for the Acme experiment. There's a proposal by Koziarev and Hutzler that outlines this entire experiment, and now we have a collaboration called PolyEDM for all these participants that are listed here, and it's going extremely well. Started with an empty lab about a year something ago, a year and a few months ago. We started building it together. Here's a CBGB cell. Here's now a signal at the very end of last year, showing that we could make the ytterbium monohydroxide. This is where we were in March 2019, right, this year. We knew this frequency very accurately, but that was it. As of May 2019, we knew this frequency. These are the laser cooling lines, excuse me. These are the laser cooling lines that will, for lasing it, cooling it into a MOT. And then we know all these frequencies. So we know a lot about the molecule now. A lot of this was in collaboration with Tim Steinley. And we were able to now, just very recently, about 3 weeks ago, do Sisyphus cooling of YBOH. And so we're less than 600 microkelvin. We're certainly much colder than that, but the way we're doing the experiment, we're not sensitive to colder temperatures. So here is kind of classic Sisyphus cooling. This is one-dimensional, and when you're blue detuned, you get this extreme cooling. This is actually just measuring the slit width for our molecular beam now. We need to measure these 3 frequencies before we can do laser cooling, do a MOT. And right now in the lab, this one, I think, is what they're working on now. Where will that put us? For poly-EDM, if you go through the numbers, assuming 10 to the 5th molecules and an optical dipole trap, puts us around there. It puts us up around here. This is post-Acme. Okay, this is not, we're going to get an EDM result after the next Acme result. Okay, and here's the group for all the experiments in my lab. Thank you.
Just before lunch, we have to vacate the room at 12, but we still have time for questions.
Given the lack of naturalness, I think was the expression you used for Susie at this point, is it time for us to start thinking about different ways of talking about EDM searches to downplay, not to change what we're doing, but is it time to start talking in a different way about the motivations?
No, yes and no. That was within the Susie framework, but if you go back, there's each one of these theories, gives an EDM prediction. So, yeah. So in the end, you're how well motivated each one of these theories are. It's very theorist dependent. The answer would be theorist dependent, but so you can just say, okay, there's this theory, minimally split Susie. Okay, it predicts it in this range. You go look for it. Is it there or it's not there?
For acne, would thorium fluoride be a good alternative?
No. No. It's not. You want the omega doublet. That omega doublet is absolutely crucial. There's that switch I was talking about. That's absolutely crucial for rejecting systematic errors, which I didn't talk very much about due to time.
Also for advanced acne, for the hexapolar lens, there's certainly some trajectories where molecules actually hit it, and the ones that hit it screw things up.
Maybe. It's a good question. Something I worry about.
Sure. The reversals, the eighth chop. Currently, how many
of noise suppression do you get from that? And then when you make these changes, do you expect to be able to, have those, like the enhanced sensitivity with longer interrogation and time and stuff? Do you expect those reversals to work as well, or is there reason to believe?
Yeah. Excellent question. I have a slide which I don't have in this stack, which shows kind of with each set of reversals, what kind of suppression you get for a particular, for at least like 2 or 3 examples. I have that. I don't have it up here, but basically some large orders of magnitude suppression. So for example, if I remember correctly, there's 2 switches which there's a slight difference in the G factor between the top set of states and the bottom set of states. But with the appropriate, and you don't know what that is precisely, but with the appropriate set of switches, you get like 5 orders of magnitude suppression because you can pull that difference in the G factors out. So it depends on the systematic error. Second question is an excellent question. So there's the systematic errors, and I didn't talk very much about those. We understood them. We thought they were under control in Acme too. So now what about Acme, the advanced Acme, the next version? Some of those, and ones we understand, we have to make some changes, okay? But technical changes to make sure that those are suppressed well below what we expect our statistical sensitivity to be. However, in every version of Acme, we found a systematic we did not expect. So whenever we quote, wherever I quote what the sensitivity is, I quote the sensitivity as statistical sensitivity for about 1 day of running, which turns out to be about what you get in the actual experiment. So the hope is that if we do see another unknown systematic, that we'll be able to suppress it the way we did in the previous 2 times. But there's no guarantee of that, of course. There are some specific systematics we'd love to talk with you about. Things like this birefringence problem we have. So you'll send a laser beam through this plate, and in fact you get this polarization gradient because of stressing of the glass due to the heat of the laser beam, and so you have to suppress that, for example. Yeah, so there's this idea of taking a buckleball and then putting this thing on it. It's for the molecules we looked at. Like there was a list. I think there was a list up there, maybe 10 different molecules with kind of alcohols on them. The Frank-Condon factors didn't change that much. However, I wanted for full disclosure, not changing that much can mean the difference between you needing 5 repump lasers and needing 10 repump lasers. And when you think about repump lasers, the other thing that's happened, which it's just a technical thing, we have one wave meter which we lock multiple lasers to within a megahertz. So this idea of scaling, you think like, oh my God, 10 lasers, but it's not that big of a deal. Certainly with YBOH, that's not the thing that scares the students. Let's put it that way. That's the best test. But so yeah, so there are. Depending on the molecule, you'll just get to the point where you won't want to laser cool it, or you better have a really good reason to, like finding dark matter.